Welcome. Today we'll explore how to find the area of a square. This is a fundamental concept in geometry that you'll use throughout your mathematical journey. A square is a special geometric shape with four equal sides and four right angles of exactly 90 degrees each. The area of a square tells us how much space is inside the square. Think of it as the surface the square covers, measured in square units. Area is always measured in square units, such as square centimeters, square meters, square inches, or square feet. The choice of unit depends on the size of what you're measuring. In the upcoming sections, we'll learn three different methods to calculate the area of a square, starting with the most common approach, using the side length. The most fundamental way to find the area of a square is by using its side length. This approach forms the foundation for understanding square area calculations. A square is a special shape where all four sides are exactly equal in length. We represent this side length with the variable s. The area formula for a square is beautifully simple. Area equals side times side. This makes perfect sense when we think about what area actually means. Since we're multiplying the same value by itself, we can write this more compactly using exponent notation as s squared. Let me show you why this formula works by visualizing the area as a collection of unit squares. When we multiply side times side, we're essentially counting how many unit squares fit inside our square. If each side has length s, then we have s rows and s columns of unit squares. This multiplication gives us the total number of unit squares, which equals the area. The beauty of this formula is its simplicity and universal application to any square, regardless of size. Remember, the key insight is that area measures the space inside a shape. For a square, this space can be perfectly divided into s times s unit squares, giving us our fundamental formula. Sometimes you might not know the side length of a square, but instead you know the diagonal. The diagonal is the distance from one corner to the opposite corner of the square. Here we can see the diagonal of our square running from corner A to corner C. This diagonal cuts the square into two equal right triangles. When we know the diagonal length, we can calculate the area using a special formula. The area equals d squared divided by 2, where d is the diagonal length. But why does this formula work? To understand this, we need to explore the relationship between the diagonal and the sides of a square using the Pythagorean theorem. In a right triangle formed by two sides and the diagonal, we can apply the Pythagorean theorem. The diagonal squared equals the sum of the two sides squared. Since both sides are equal, we can simplify this to d squared equals 2 times s squared. Now we can solve for s squared. Dividing both sides by 2, we get s squared equals d squared divided by 2. But remember, the area of a square is s squared, so we can substitute and see that the area equals d squared divided by 2. This is exactly our diagonal formula. To make this even clearer, if we know the diagonal is d, then each side length is d divided by the square root of 2. This comes from rearranging our Pythagorean relationship. We can verify our diagonal formula by substituting this expression for s into the basic area formula. Area equals s squared, which becomes d squared over 2. This diagonal method is particularly useful in real-world situations. For example, if you're measuring a square room and can only measure the diagonal distance, you can still calculate the floor area using this formula. Remember, this formula works because the diagonal creates two right triangles, and the Pythagorean theorem connects the diagonal length to the side lengths. In our next section, we'll explore how to find area when we know the perimeter instead. Sometimes you might only know the perimeter of a square, which is the total distance around all four sides. The good news is that you can still find the area using this information. Remember that a square has four equal sides. If we call the length of each side s, then all four sides have the same length. The perimeter is the sum of all four sides. Since each side has length s, the perimeter equals ss plus s plus s. This simplifies to perimeter equals 4 times s, or simply 4s. Now, if we know the perimeter, we can work backwards to find the side length and then calculate the area. Step 1 is to find the side length. Since the perimeter equals 4 times the side length, we can solve for s by dividing the perimeter by 4. Step 2 is to calculate the area using the basic area formula. Once we know the side length, we square it to get the area. We can substitute our expression for S into the area formula. Substituting S equals P over 4, we get area equals P over 4 all squared. This gives us a direct formula for finding the area of a square when we only know the perimeter. Here's our complete formula for finding the area of a square from its perimeter. This works because a square has 4 equal sides, so dividing the perimeter by 4 gives us the side length, and then we square that to get the area. The key insight is that knowing the perimeter gives us enough information to find the side length, and from there we can calculate the area using the fundamental relationship that area equals side length squared. In the next section, we'll see this formula in action with a concrete example. Now that we understand the basic formula for finding the area of a square, let's work through our first example step by step. Here's our problem. We need to find the area of a square that has a side length of 7 centimeters. First, let me draw the square and label its dimensions. We can see that each side of this square measures exactly 7 centimeters. To find the area, we use the fundamental formula for the area of a square. Area equals S squared, where S represents the length of one side. Step 1. We substitute our known side length of 7 centimeters into the formula. So area equals 7 squared. Step 2. Remember that 7 squared means 7 multiplied by 7. This is because we're finding the area by multiplying length times width, and in a square, both dimensions are equal. Step 3. Now we perform the multiplication. 7 times 7 equals 49, and this is where we must remember to include our square units, 49 square centimeters. To help visualize this result, imagine dividing our square into a 7 by 7 grid of unit squares. Each small square represents 1 square centimeter, and we can count exactly 49 of them. This visual representation helps us understand why the answer is 49 square centimeters. The key takeaway is to always remember to include square units in your final answer. This tells us we're measuring area, not just a regular number. Now that we've mastered finding the area using side length, we're ready to explore more complex examples using different given information. Now we'll work through our second example, where we need to find the area of a square when we're given the length of its diagonal. Here's our problem. We have a square with a diagonal that measures 10 inches, and we need to find the area of this square. Here's our square. The diagonal is the line that connects two opposite corners, and in this case it measures 10 inches. Remember, when we know the diagonal of a square, we use the formula area equals d squared divided by 2. Now let's solve this step by step. We'll substitute our known value into the formula and calculate the result. Step 1. We substitute d equals 10 into our formula. This gives us area equals 10 squared divided by 2. Step 2. We calculate 10 squared. Remember, 10 squared means 10 times 10, which equals 100. Step 3. Finally, we divide 100 by 2. 100 divided by 2 equals 50. Therefore, the area of our square is 50 square inches. Notice how we include the proper units, square inches, because area is always measured in square units. This formula works because of the relationship between a square's diagonal and its sides. The diagonal creates two right triangles, and using the Pythagorean theorem, we can derive that the area equals d squared divided by 2. This completes our second example. We successfully found that a square with a 10-inch diagonal has an area of 50 square inches. Now we'll explore one of the most fascinating properties of squares. For any given perimeter, a square always encloses the largest possible area compared to any other rectangle. To understand this principle, we'll examine several rectangles that all have the same perimeter of 20 units, but different dimensions. First, consider a very thin rectangle with dimensions 1 by 9 units. This gives us a perimeter of 2 times 1 plus 2 times 9, which equals 20 units. The area is 1 times 9, which equals 9 square units. Next, we have a rectangle with dimensions 2 by 8 units. Again, the perimeter is 2 times 2 plus 2 times 8, which equals 20 units. But notice the area is now 2 times 8, which equals 16 square units, already larger than our first rectangle. Moving closer to a square, we have a 3 by 7 rectangle. The perimeter remains 20 units, but the area increases to 3 times 7, which equals 21 square units. Finally, we reach the square with dimensions 5 by 5 units. The perimeter is still 20 units, but now the area reaches its maximum value of 25 square units. Notice how the square highlighted in teal has the largest area of all rectangles with the same perimeter. Now let's understand the mathematical reasoning behind why this happens. We'll examine the general case where we have a rectangle with a fixed perimeter. For any rectangle with perimeter P, if we call the length L and width W, then P equals 2L plus 2W. This means L plus W equals P divided by 2, which is a constant. The area of our rectangle is L times W. Since L plus W is constant, we need to find when the product L times W reaches its maximum value. The key insight comes from the arithmetic mean geometric mean inequality. The arithmetic mean of L and W, which is L plus W divided by 2, is always greater than or equal to the geometric mean, which is the square root of L times W. Equality occurs only when L equals W, meaning when our rectangle is actually a square. Therefore, we can conclude 3 important points. First, equal distribution of the perimeter among all sides maximizes the enclosed area. Second, any deviation from a square shape will result in a smaller area. And third, this principle is fundamental to many optimization problems in mathematics and real-world applications. Let's see this principle in action with a dynamic demonstration. Watch as we transform a rectangle while keeping the perimeter constant. Starting with a 1x4 rectangle, we have an area of 4 square units and a perimeter of 10 units. Now watch what happens as we gradually make the rectangle more square-like while keeping the perimeter constant. As the rectangle becomes more square-like, approaching dimensions of 2.5 by 2.5, the area increases to 6.25 square units, while the perimeter remains exactly 10 units. This demonstrates that the square shape maximizes the enclosed area for any given perimeter.